Hello and welcome. We are starting a new unit in calculus, the unit of derivatives. So what is the derivative of a function? Another word for the word derivative can be the word speed, because the derivative of a function actually will tell us the speed of change of the y values in a function. In addition to that, though, the derivative of a function will also give information about whether the y values are increasing or decreasing. So whether the speed is going to be positive or negative. So a better word than to describe derivatives would be the word velocity. Remember that speed is a scalar quantity. It tells us the size of a quantity. And velocity is a scalar and a vector quantity, so it will give information about the size of it, so we will know how fast the function is changing, and the direction of it, so it will give us information about whether the function is increasing or decreasing. Now, if you remember in the previous unit, very often we use the word instantaneous rate of change. And what instantaneous rate of change actually gave us was how fast the values of y were changing at a specific point. And it was measured by the slope of the tangent at a point. Now remember that instantaneous rate of change is also another word for the speed or the velocity of a function at a point. So we're going to say that the derivative of a function is nothing but the speed of change of the y values of a function, or the velocity, even better, or instantaneous rate of change of a function, or the slope of the tangent at a point on the graph of a function. And the derivative of a function is denoted by this symbol. So if we're given the function f of x, we add a small apostrophe here, and this is read as prime. So we say that the instantaneous rate of change of a function, which is measured by the slope of the tangent at a point, actually is the derivative of a function, or f prime x. So as you can see, the concept of the derivative is built on IROC, instantaneous rate of change, and slope of tangent. So we're going to say that given a function f of x, the derivative of f of x with respect to x is the function f prime x, which is defined by the slope of the tangent at x. And remember that the slope of the tangent at x is measured by the limit as h approaches 0 of f of x plus h minus f of x divided by h. Now, this limit is a formula that will help us discover the derivatives in every group of functions. You can think of it as the table of values helped us discover the shape of each group of functions when we graph them for the first time, right? And after that, we discovered other ways to graphing them. But the table of values was the first one. Now, this formula will be the very first tool that we are going to use initially to explore the derivatives in every group of functions. And that is the reason why we give this formula a very special name. This is called the first principles formula. Okay, so as we study each group of functions, like polynomial, rational, etc., we're going to learn how to find the derivatives using a specific formula for each group of functions. But this formula here, the first principles, will help us discover those special formulas for each group of functions. So, what is the interpretation of derivatives? What is the meaning of derivative? So the derivative of a function is the slope of a tangent of a function at a point, so on the graph of a function at a point, or it is the rate of change, the instantaneous rate of change at a point. So we're going to get started here with practicing how to determine the derivatives in various functions. As examples, I brought in a quadratic and then a rational, and later on we are going to try a square root function. So to find the derivative of f of x equals 2x squared minus 13x plus 35 at any point a means that we need to find f prime at a. And f prime at a is measured as the limit as h approaches 0 of f of a plus h minus f of a divided by h. So we'll now start by substituting f of a plus h, which in our case will be, remember that this is f of x. Wherever you see x, now you will replace it with a plus h. So that would be 2 times a plus h squared minus 13 times a plus h plus 35. So this will be f of a plus h. And then minus f of a, so which means that wherever we see x, now we're going to write a in the equation of the function. So minus 2a squared minus 13 times a plus 35. Now remember that we need to keep these numbers here in brackets, and the minus sign will apply to every term inside the brackets. And that will be divided by h. And now we have to simplify. Remember, there is a lot of algebra involved in evaluating the derivatives. So what that means is that we have to be prepared for it. And we have to think we have a lot of work to do, because that's how we can embrace the work, number one, and actually be more patient as we work and do a better job, obviously, as a result. So this would be 2ah plus h squared here. So I'll just expand perfect squared minus 13a minus 13h plus 35 minus 2a squared plus 13a minus 35. Okay, so we're removing the brackets there. Sorry. It has to be perfect, you know? And now we are going to start simplifying as many terms as possible. So what I do see in here is 13a and negative 13a. I also see plus 35 and minus 35. And here we go. We have here the limit as h approaches 0. Another long line for this very long expression. And we have 2a squared plus 4ah plus 2h squared minus 13h minus 2a squared all over h. Okay, so I'm going to take my work here now. And we're going to simplify some more. Now remember that whenever you find the derivative of a function, all the terms in the numerator, all the terms that have no h will simplify. Okay, so the only terms that will be left in the numerator here will be terms that have h as a factor. It can be power 1, power 2, power 3. It depends on the function. But what I'm trying to say in here is that this 2a squared and negative 2a squared will simplify. And as you can see in here, we end up with terms that all have an h in it, okay? And that is the h that will simplify the h in the denominator. If we end up with terms that have no h in the numerator, that means we have to go back and check our solution. So maybe we made a mistake somewhere, and it can happen. So for AH, and since we're here, we can factor the H, but I'm going to take the long way so that I won't lose anyone in the process here. So, but you will see that with practice, there are steps that you will find that very easy to do, like in between. So this would be H 4A plus 2H minus 13. Okay, that's over H. And now it's time to say goodbye to H. So goodbye, H. And we have the limit as H approaches 0 of 4A plus 2H minus 13. Now we can let H be 0. No problem. So 2 times 0 minus 13. So we ended up with 4A minus 13. And this will be F prime at A. So what does that mean? So what does this formula give us? This formula will give us a way to find the derivative of a function at any point A. The derivative of a function, remember, measures the speed of the function. The speed won't be the same at any and every point on the graph of a function. So it will depend on where we're measuring that speed, right? So, and this formula will allow us to find the speed at any value of A. So the second question is asking us to use the derivative that we found from part A, so the derivative that we just found here, in order to determine the slopes of the tangents to the parabola when x equals 1, 2, 3, or 4. So in other words, we're given here that A equals 1, which means f prime at 1 would equal 4 times 1 minus 13. So this would equal 4 minus 13, negative 9. Now, x equals 2 means that we are measuring the slope of the tangent at 2. Slope of the tangent means the derivative at 2. So that means we have 4 times 2 minus 13. Remember, we are using the same formula, this formula, to find all these derivatives. So f prime at 2 would be equal to 8 minus 13, negative 5. So here A equals 3. Again, remember that f prime A equals 4A minus 13. So that be 4 times 3 minus 13. So f prime A equals 12 minus 13, negative 1. And last, A equals 4. We know f prime of A equals 4A minus 13, which tells us that we have 4 times 4 minus 13 here. 16 minus 13 equals 3. So we're going to say f prime at 4 equals 3. And actually, I'm going to highlight all these. And I'm going to move on to the next question to identify whether the function is increasing or decreasing at each point. Okay? So if you looked at the graph of this function, sorry, just want to check something. Okay, so if we looked at the graph of this function, which I am going to actually put in here on Desmos right now. So we have y equals x squared, 2x squared. Let me see here. Minus 13x plus 35. Okay, so here is the graph of this function. Okay, and we measure the slope of this function at the following points. I just want 1 squared to equal 1, so it's easier. So at x equals 1, you can tell that the value of the slope of the tangent is quite a big negative, right? Because the function is quite steep, decreasing very fast. And at x equals 2, the steepness is smaller. At x equals 3, the steepness was about -1. And at x equals 4, the steepness was positive, or the tangent had a positive slope. All right? So it kind of relates or connects the values we found with the function, the graph of the function. Now, if the parabola was in this shape, and here were the points 1, and then here was point 2, here was 3 very close, and here was the point 4 somewhere, okay? So we are going to say that at this point, the derivative is negative, or the slope of the tangent is negative, the function is decreasing. Negative slope, decreasing function. Negative slope, decreasing function. At a positive slope, the function is increasing. So we're going to say that if we want to identify whether the function is increasing or decreasing at a point, we must remember that if f prime x is positive, then f of x is increasing. And if f prime x is negative, then f of x is decreasing. Which means that at x equals 1, f of x will be decreasing. Why? Because f prime was negative. At x equals 2, f prime x was negative because it was -5, right? So therefore, f of x is decreasing. At x equals 3, again, f prime of x was -1, so that's less than 0, which makes the function f of x, again, decreasing at that point. And last but not least, at x equals 4, we found out that f prime was +3, so that's a positive number, which makes f of x increasing at that point. So in the same way, now we're going to move on to the next part, differentiability of a function. Now, I always suggest my students that whenever you are learning something new, whenever you move on to a new topic within a lesson, try to revise or try to review what you've learned in the previous page. You know how math is related, right? So, and when we keep in touch with what we are learning, then we can continue with more confidence. So here we go. I'm going to say on this first page of the lesson, I just learned the concept of the derivative. It means the speed, or even better, the velocity of the function. It tells me how fast it is changing, or in other words, it gives me the instantaneous rate of change of a function at a point, which I know is measured by the slope of the tangent at a point, which I know is measured by this limit. But today I learned that this limit is used for discovering any rate of change in any function, instantaneous rate of change in any function. It's called the first principles formula. And we analyzed in here a quadratic function, and we found out that, or we emphasized the fact that when the derivative of a function is negative, then the function will be decreasing. When it's positive, the function is increasing. And I also noticed that the derivative of a function can be another function. Notice here, f of x is a quadratic. The derivative of it at any point can be a linear function, okay? So we're moving on to the differentiability of a function. The word differentiability is ability to be differentiated at a point. Okay, it has the word ability in it, right? So, which I actually have misspelled here. So there is an I missing. So, well, just to keep things interesting, what can I say? So, a function is differentiable at a point if we're able to evaluate the derivative of a function at a point. So we're going to say that a function is differentiable if f prime of a exists, which means that graphically, when can f prime exist? When we are able to draw the tangent and there is only one tangent at that point. And algebraically speaking, we're going to say that the tangent drawn has a slope of measurable value. So we are able to evaluate the derivative at that point. Okay? So I'm going to write this. Function at a point. And we're going to take a look at an example here of a rational function, gt equals t over t plus 1. And we have to find out at what point is the function non-differentiable and explain why it's not differentiable. So I'm going to get started with g prime t. We know that this is measured as the limit as h approaches 0, fraction g of t plus h, minus g of t divided by h. So this would equal the limit as h approaches 0, long fraction. Leave a lot of room in the meantime because we're going to have fractions inside fractions. So again, as we mentioned before, so wherever you see t, now you will replace it by t plus h. So I'm going to have a fraction here. So t plus h over t plus h plus 1 minus g of t is t over t plus 1. And that is going to be over h. Now first we need to take care of the numerator. And as you can see in here, we have two fractions with different denominators, which means the denominators don't have a common factor, and which in addition means that the lowest common denominator then must be the product of the two. So t plus h plus 1 times t plus 1. So what that means is that this denominator here is going to need a t plus h plus 1. And obviously, both numerator and denominator will get the same thing. And this denominator here is going to need a t plus 1. So both numerator and denominator are getting the same thing. So now we can write them under the same denominator, which is t plus 1, t plus h plus 1. And in the numerator now, we're going to have to expand each of them. Let me make this a little longer. So we'll have t squared plus th plus t plus h. Okay? So t squared plus th plus t plus h. And then we have minus t squared minus th plus 1. Remember that this minus sign in here, right? You can think of it as the minus before t, right? So minus t squared minus th minus t. And all this will be over h. And if you want to make it look like a fraction over fraction so we can see the division a little better, then that's totally fine as well. So now we have the limit as h approaches 0, long fraction here. We have t plus 1, t plus h plus 1. And we're going to check and see if we can simplify anything in the numerator. Remember, we expect to get rid of all the terms that have no h in it. So t squared and negative t squared simplify. Negative t and positive t simplify. And we also have th's that simplify in this case. So we're left with just h in the numerator. Okay, that's lovely. And all this will be over h, over 1 if you wish. Now remember that this would be our big fraction, and it's time for us to divide. And when you divide two fractions, we change the division, the main division, into multiplication, and you reciprocate the denominator h over 1. So this will turn into h over t plus 1, t plus h plus 1 times 1 over h. And now this is the exciting part. Goodbye h. You can't bring us trouble anymore. And we have the limit as h approaches 0 of 1 over t plus 1, t plus h plus 1. And now we can make h equal to 0. No problem. That would be t plus 1, t plus 0 plus 1. Even better, 1 over, I really want to make this line a little straighter. Or you can obviously write this as, the name of this function was g, I think, or yes. So we can write here g prime t equals 1 over t plus 1 squared. Now let's take a look at the rest of the questions asked in this particular example. So the question is asking at what points is the function non-differentiable? Okay, so if we are asked at what point the function is differentiable, we have to check with the derivative of the function, okay, because we are discussing differentiability. So let's take a look at the derivative of the function. We said that g prime t is 1 over t plus 1 squared. Is there any point on the, or any value of t that makes this particular equation undefined? So remember, this is a rational function in itself, and at t equals negative 1, the denominator will become 0. And denominator being 0 means that g prime at negative 1 will be undefined. So we're going to say that it's undefined at negative 1. But what is the reason why it's undefined at negative 1? What exactly happens to the graph of the function? Look at the graph of the function again. So t equals negative 1 is a restriction in the graph of this function, and you can easily actually deduce here that there is a vertical asymptote right at t equals negative 1. And if you graph this function actually at negative 1, there is an asymptote. And because it's impossible to draw a function or a tangent at a point where the function is undefined, because there is no point where we can actually draw the tangent, that's the reason why we say that the function is non-differentiable at 1. Okay? So this is one of the reasons or one of the cases when we see functions being non-differentiable at a point. So a function is non-differentiable at a point where it's undefined at one, when it has an asymptote, if you want to look at it from the graphical point of view. Now we're going to look at the second example. In the second example, we have a radical function. And what we want to do here is find the derivative and find the intervals where it's non-differentiable and explain why. So we're going to start with r prime x, which is the limit as h approaches 0, first principles formula, right? Doesn't matter what kind of equation or what kind of function we are working with, right? The first principles formula will always be there for us to help finding the derivative. So Rx over h. So that would equal the limit as h approaches 0. And here we go. We have the square root of x plus h 5 times minus 8. So wherever you see x, you replace it by x plus h, right? Because we're finding r of x plus h minus the square root of 5x minus 8 divided by h. I will try to simplify the numerator as much as I can. Okay. So we have the square root of, let me try this. I'm going to draw the perfect square root there. Thanks, good notes. And then minus the square root of 5x minus 8. And then over h. Now, as you can see in here, we ended up with an indeterminate form limit, because we cannot substitute h by 0 at this point. And it involves radicals, right? And a fraction, obviously. So remember how we evaluated such limits, right? So we multiplied by the conjugate of the numerator. Now, why do we have to do this? The goal is to simplify h in the denominator. To simplify h in the denominator, we're going to need an h in the numerator. Okay? So we don't have an h in the numerator, or should say we do have one, but it's inside the root, and we cannot access it like right away. We cannot just grab it outside the root. So we need to remove the roots, and this is done very nicely with the help of the conjugates. It's something we have discussed in the past, so if you have questions about it, just look at the previous lessons about limits. So that would be the root of 5x plus 5h minus 8. Now, remember that if you have a minus, so the difference, the conjugate will be the sum of the exact same terms. So 5x minus 8. And we have to do the same thing to the denominator, obviously, because that's the rule. We cannot multiply just one side of the fraction and not the other, right? So, okay. So let's see what we get now. So this would be the limit as h approaches 0, long line. And we have h, and we have the root of 5x plus 5h minus 8 plus the root of 5x minus 8. Now, our numerator is going to change a bit more than the denominator. So we have 5x plus 5h minus 8 squared minus the square root of 5x minus 8 squared. So that's the difference of squares formula, right? So you can look at these two things, the square root and the square, right, as two things that simplify each other. Wherever they go together, they would just make each other disappear. So that's because the square root is a power of half, and the power of 2 and the power of half will multiply to 1, right? So now we have 5x plus 5h minus 8 minus 5x minus 8. I will emphasize again one more time that you have a minus here, and you're minusing a binomial, so you got to keep that binomial in brackets. It's a source of many innocent mistakes. So down here we have h, and we still have this conjugate. We're just going to sit here for a while until we reach to the end of the limit evaluation here. So root of 5x minus 8. And we can simplify a little bit more now. So limit as h approaches 0. I know I'm taking the steps slowly just because I want to show everything and explain and make sure that everything is clear. But obviously there are steps that you would like to skip, right? So, for example, you can just go from here to here right away, right? So here we go. We have h. And again, we have this root thingy. And, you know, remember when I said you got to be patient with these expressions because they're long, some repetitive, some are sitting there and waiting for something to happen, right? So like this conjugate. So I'm going to take this up here. That was one ugly line. Okay, so let me just make this a little prettier. And we have the limit as h approaches 0. Remember that we are trying to find r prime x. So let's rewrite it. And in the numerator, we have terms we can simplify, hopefully. Let's see. So we have 5x and negative 5x, negative 8, positive 8. So goodbye to them. And numerator has just 5h. Yay. So 5h. So h is a factor. H is a factor in the denominator as well. We still have this beautiful conjugate that we keep on writing because we have no choice but write it. And then plus root of 5x minus 8. And the exciting part, say goodbye to h. And this will be ready to evaluate, so that would be 5 divided by the square root of, 5x plus 5 times 0 minus 8 minus root of 5x minus 8, which will give 5 over, remember that this will be 0, so we have a root of 5x minus 8, plus the root of 5x minus 8. So we have two roots of 5x minus 8, so we're going to say r prime x equals 5 divided by 2 roots of 5x minus 8. Okay, so this is the derivative of r prime x. Now, let's move on to the next question asked here. At what intervals is the function differentiable? So this is how you would translate it in your head. At what x values is this function defined, r prime x? So notice that you have a denominator. There is a risk of denominator becoming 0 at x equals 8 over 5. So if x equals 8 over 5, then the function is non-differentiable. Another thing we have in the denominator, or a special thing we have, is the root. We want the expression inside the root to be positive. So we're going to say that, if 5x minus 8 is a negative number, that won't work. So we don't want it to be negative. We don't want it to be zero. So at 8 over 5. So we don't want 8 over 5 for x. And in other words, we're going to say that 5x minus 8 has to be positive. Not 0. So that means that x has to be bigger than 8 over 5. So we're going to say that the function is differentiable for the x values bigger than 8 over 5. Now let's take a look at the graph of the function at 8 over 5. So what happens at 8 over 5? At 8 over 5, this is a graph of Rx, by the way. And at 8 over 5, which is right here, the function will have an asymptote. Will have, the tangent, right, that we can draw actually. It's a legitimate tangent actually. You can draw a tangent right here. I don't think I want to write it this way. Let me make it a straight line, because okay, so this would be the tangent line. So at x equals 8 over 5. So at this point, we are able to draw the tangent, but the problem is that the tangent is vertical, and vertical lines have undefined slopes. And you can think of the undefined slopes at the vertical lines as steepness of maximum, or slopes with, or lines with maximum steepness. Sorry, I was struggling there for the word. So these are slopes with, or tangents with maximum steepness, okay, or lines with maximum steepness. And maximum steepness is a steepness of infinity, and infinity is a number. It's an undefined number, so it's a concept. It's not even a number. So that's why we say that the function is non-differentiable at 8 over 5. One more example to go. We're going to talk about f of x equals absolute value of x. We're going to show that f of x equals absolute value of x is non-differentiable at 0. So I'm not going to worry about the second part of the question. We're talking about the derivative, so before I decide, or I judge about, or make a judgment about differentiability at 0, I have to find the derivative, see what I get first. So we're going to say that if I want to find f prime of x, that means I have to find the limit as h approaches 0 of f of x plus h minus f of x over h. Now, we are differentiating exactly at 0, right? So that means x value equals 0. So I will make the adjustments to my formula. So we're going to say that would be f at 0 plus h minus f of 0 divided by h. And now I will substitute f of 0 plus h. That would be the limit as h approaches 0. And wherever you see absolute value here, wherever you see x, you have to substitute by x plus h, or 0 plus h. So that would be absolute value of 0 plus h minus absolute value of 0 divided by h. So this will turn into the limit as h approaches 0, absolute value of h minus 0 over h. Or even better, we're going to say that f prime at 0 equals the limit as h approaches 0 of absolute value of h over h. So in order to find the derivative, we need to evaluate this limit. Now, this is an indeterminate form limit because it's undefined at 0. You get 0 over 0. And also, now the special thing about this limit is that it involves absolute values. We cannot evaluate any function or any limit of a function with the absolute values in it unless we remove the absolute value. And remember that to remove the absolute value, we have to consider two cases. Case number one, if h is positive or 0, but in this case 0 is an undefined point, then we're going to say that the absolute value of h will be calculated as the absolute value of a positive number, so it will equal that positive number that is inside it. So therefore, we're going to say that the function h over h can be written as positive h divided by positive h. So that means that the limit as h approaches 0, now another detail we need to add in here is if h is positive, that means we can only approach 0. So if it is bigger than 0, we can only approach 0 from the right-hand side because we are approaching 0 to find the limit, right? So we're going to say when we approach 0 from the right-hand side, the absolute value of h will be the absolute value of a positive. So it will equal that positive number. So we're going to have h over h, which is the limit as h approaches 0 of 1. So that's the limit of a constant. It will equal 1. Now, case 2. So, case 2 scenario is if h is a negative number. If h is a negative number, it means that the h values will approach number 0, the point where we're evaluating the limit, right, from the left-hand side. And the absolute value of h will equal, remember this is the absolute value of a negative number, right, will equal the opposite of that negative number. So remember this will turn out into a positive because h in itself is a negative number. So therefore we're going to say that the absolute value of h divided by h would be negative h over h. So the limit as h approaches 0 from the left-hand side of the absolute value of h over h would equal the limit as h approaches 0 from the left of negative h divided by h, which equals negative 1. So we just found that the right-hand side limit is 1. The left-hand side limit is negative 1. So we're going to say that the limit from the left and the right don't agree with each other. So one is giving one value, one is giving an opposite value. So 1, 1, 1, negative 1. So we can't tell for sure what the limit will be at exactly 0. And when we can't tell what the limit will be exactly at 0, it means that the limit is undefined. Remember, this limit measured the derivative of the function at 0. So we're going to say that the derivative at 0 doesn't exist because the left and the right didn't agree. And let's take a look now at the graph of the function. So the graph of the function y equals absolute value of x is this V shape with a 90-degree angle in between. Look at the rate of change of this function as we approach 0 from the left-hand side. So when you approach 0 from the left-hand side, the rate of change of a function is negative 1. The function reaches a point here, and on the other side of 0, the function changes the speed abruptly to a positive one to the opposite. So that makes it impossible for us to draw a tangent at this point, because we will know if the left and the right is going to be approximately the same limit, right? So that would be undefined. Now, that's why we say that the function is non-differentiable at 0. Now, in calculus, these kind of points, like 0 at absolute value of x, are what we call corners. And whenever the graph of a function, whenever the graph of a function has a corner, wherever it has a corner, it will be non-differentiable at that corner, at that point, at that x value where the corner happens. Okay, so this is the first part of lesson 1, the derivatives. And I hope you enjoyed the lesson, and I hope that you made something out of it, and then saw the connection between how the derivative can actually appear in various functions. And please stay tuned for the part 2 of lesson 1 on derivatives. Thanks for watching, and thanks for listening. Bye for now.